has spent 8 significant years studying the feasibility of jet reaction controls for vertical takeoff and landing airplanes. In 1947, Ryan received its first research contract for work in this field. Since that time, jet VTO development has become increasingly important to the military services. Ryan is currently building 2 jet-powered VTO aircraft for the Air Force. These airplanes, the first of their kind ever constructed, are to be used entirely for research purposes. Their military designation is X-13. Their function is simple: to demonstrate the complete practicability of jet reaction controls for vertical takeoff and landing. Though the Rolls-Royce Avon engine is capable of developing 10,000 pounds static sea-level thrust, the research X-13 airplane is designed to operate at relatively low speeds and at low altitudes. Fixed landing gear is provided so that the pilot can take off and land in a conventional manner during initial flights. As soon as the pilot becomes familiar with the airplane in level flight and with its behavior in transition and vertical flight at altitude, the fixed landing gear will be removed. A belly hook will then be installed to permit takeoff from and landing on a vehicle as currently proposed for the tactical VTO airplane. This is the first of a series of Ryan VTO progress reports on film. This initial report deals with fabrication of the first of the 2 X-13 research airplanes, as well as with preparations for flight testing. The report is divided into 2 parts. The first portion shows early fabrication activity prior to June 1st, 1955. The second part shows some modifications effected, various types of testing, and flight preparations which took place between June 1st and August 1st. Fabrication of the first X-13 began simultaneously on the fuselage and the tank assembly integral to the delta-shaped wing. Here the tank takes shape on a small vertical jig. Meanwhile, other components of the airplane begin to fill various jigs and fixtures throughout the shop. In this scene, the vertical fin becomes recognizable. The X-13 fuselage is conventional in construction. Transverse bulkheads, longerons, and skin are made from aluminum alloys, with the exception of the aft end of the fuselage, which is constructed of titanium. An unusual feature of this airplane is the large size of the engine for a relatively small aircraft. The finished wing is ready for mating to the fuselage. Because of careful design and precision tool manufacture, wing and fuselage mate perfectly, even though this is the first time they have been brought together. Some equipment begins to find its way into the airplane. Here is the nose of the X-13, showing a small part of the electrical equipment and wiring. Cockpit design of any new airplane is a critical problem. The relative simplicity of the X-13 is evidenced by the appearance of the finished cockpit. Only instrumentation basic to the operation of the airplane is included. The ejection type pilot seat is shown beside the aircraft. When installed, the seat can be rotated 45 degrees forward as the attitude of the airplane approaches the vertical. The fixed landing gear is designed for easy removal when the later phases of testing begin. Light in weight, the gear is designed to carry the 7,000-pound airplane with a 3G limit landing load factor. Soon after June 1st, mechanics installed a checkout engine in the fuselage of the X-13. The engine was later replaced with a fully qualified flight engine, the Rolls-Royce Avon RA-28-49, weighing approximately 2,800 pounds. A full load of fuel plus the engine accounts for considerably more than half the weight of the entire aircraft. Diversion of the exhaust stream by means of a gimbaled nozzle provides pitch and yaw control in vertical flight and supplements aerodynamic control forces during transitions. Basic fabrication is nearly complete. The contour lines of the X-13 airplane are seen for the first time. The main engine air intake duct had to be designed for the relatively low speeds of this particular airplane. The final configuration involved considerable wind tunnel testing. The entire ducting system of the X-13 posed unusual design problems because of the low flying and hovering speeds, as well as the unconventional flight attitudes of the aircraft. Roll control is achieved by diverting compressor bleed air through ducts to differentially rotating elbows in the wingtips. Note the magnitude and speed of elbow rotation. Outside hydraulic power is provided for an early hangar check of flight controls. Here the elevons are being tested. While finishing touches are being put on X-13 number 1, across the shop in the static test jig, X-13 number 2 is being rigged for testing. Here specified loads are applied to the structure to prove its worthiness for flight. The static test jig is a maze of loading straps, weights, wires, and gauges. As high as a two-story house, it offers the best possible means of structurally evaluating the overall airplane. Meanwhile, on July 13th, the heavy hangar doors are rolled back and the completed number 1 airplane is moved to the test area to begin ground engine runs. Though it is to go but a short distance, it is carefully covered. Positioned and tied down in the engine test area, the paper wrapping is removed and the airplane readied for the first engine runs. The Rolls-Royce Avon engine has been tested in a test cell, but this is the first time it has been run up in the airplane itself. More than merely an engine is being tested. Engineering personnel will be watching the airplane carefully to note the effect of a full power run-up on structure and airplane systems. An engineer stands by to check compressor bleed air as the engine is revved up. At 96% of full power, the blast actually buckles the deflector set up to channel the jet stream out of the enclosure. With engine runs completed, the airplane is made ready for vibration tests. Vibrating gear and recording equipment are moved in and set up. The purpose of a vibration test is to determine information concerning the critical flutter speed, the speed at which the airplane can literally shake itself to pieces. Small vibrators are installed at the wingtips and elsewhere and activated at increasing frequencies. By this procedure, the resonant frequencies upon which the critical speed depends can be determined. Since flutter is a function of airplane rigidity, among other factors, the more rigid the structure, the higher the critical speed. The X-13's critical flutter speed is far above its maximum speed. Meanwhile, testing continues with the tethered test vehicle. This test vehicle serves both to perfect control components and to improve pilot proficiency in hovering and vertical flight. At the end of the present reporting period, the first X-13 was completed and ready for the development engineering inspection. The second X-13 was approximately 50% through its proof test program.